Okay, let's look at f. When I look at f, let's make an observation that we have the difference of perfect squares here. And if this x were not in the denominator, if it were just out front like this actually would be a regular substitution problem, kind of like what we did in part D of this, up above. But the x is in the denominator, right? So that's like an x to the negative 1. So that's not going to help us. If we tried to let u equal x squared minus 4, our du would be 2x dx, and this x to the negative 1 is never going to get used. So we do have to do a trig substitution. The fact that it's a difference of perfect squares tells me that the square root goes on one of the legs. So if I choose it here, and again it's a choice, then my hypotenuse is x and this other leg is 2. I could alternatively put the 2 here and the square root here. But with this choice, notice that my x over 2 is my hypotenuse over my adjacent. So that's the secant. If I do it the other way around, it's going to be cosecant. So I'm going to stick with this one. Okay, multiplying both sides by 2, we get x is 2 times secant of theta. And so dx is 2 times secant tan d theta. So when I go to replace everything in terms of my variable, in terms of my thetas, I can either do directly that x is 2 secant theta, or I can go back to my triangle and say I'm trying to come up with something that represents the square root of x squared minus 4. Let's use the other side as the simplest one. Let's make that 2. So what's opposite over adjacent? That's tangent. So multiplying both sides by 2, the square root of x squared minus 4 is equal to 2 tangent of theta. Again, the other choice would be to write x as 2 secant of theta squared, and then actually just do this out. So we'd get 4 secant squared theta, and then that's 4 times secant squared minus 1, and that's 4 times Pythagorean identity tangent squared, and then finally we get to 2 tangent of theta. So we get the same thing either using the triangle or using the Pythagorean identity. Okay, so however you want to look at it, we have 2 tangent of theta in the numerator. X is 2 secant of theta. That's my denominator. And don't forget the ever important dx, because without it, things won't cancel. Well, not likely. All right, let's just divide that. So the 2 secants cancel, and I'm left with a 2 times tangent times tangent. So that's tangent squared of theta. Now, I don't know how to take the antiderivative of tangent squared because, well, it's tangent being squared, right? That makes things harder. But if I recognize the Pythagorean identity that tangent squared is equal to secant squared minus 1, that becomes something I easily can find the antiderivative of, right? Because the antiderivative of secant squared is just tangent, and the antiderivative of 1 in terms of theta is theta. And so there you have it, the antiderivative. I believe that's also one we did earlier in the notes. Okay, so last but not least, we rewrite in terms of x. Tangent of theta is this thing right here, right? So that's the square root over 2 minus theta is inverse secant of x over 2. By the way, if you said theta was something like inverse tangent of this expression, that also would be true, right? So the point is you really can write 6 different expressions that represent theta, one for each of the 6 trig ratios, and they all would be true as long as you use the appropriate side. So if you wanted to distribute this 2, you can. That would cancel it in the first term, but then you'd have this extra 2 here. So I don't really care. However you want to look at it, those are both fine. So hopefully that one made okay sense to you.